Today we'll discuss how momentum helps neural networks learn faster and more smoothly. Let's explore optimizers. So optimizers are algorithms that improves the gradient descent learning. So we know about the vanilla gradient descent algorithm, right? So we initialize the learning rate and we start with 0th iteration. We choose some random initial weights and then we iterate until convergence. At each iteration, we compute the gradient of the error or loss function. Then we update the weight parameter. Wt plus 1, that is the weight at iteration t plus 1, is equals to Wt minus alpha times gradient of this error at iteration t, the previous iteration. And we increment the iteration and we do this until convergence. So our target is to minimize the error or loss. So let's say this is the convex error graph we have and this is the minimum point. So we can start at any point, we have to reach to this minimal point. If we start from here, we have to go in this direction. If we start from here, we have to go in this direction. So that's how we do the gradient descent. And one more quick thing is, at this point, let's say this is the gradient, is the slope, right? So this is a positive gradient. So if the gradient is positive, and we have to move in this direction, negative direction. At this point, gradient is negative. In this case, we have to move in the positive direction. So that's why we are deducting learning rate times the gradient. And after convergence, we'll get the W star, the optimum weight, and that will be the weight after tth iteration. Now this is the vanilla gradient descent. This is not that useful. In our previous videos, we also talked about batch gradient descent, stochastic gradient descent and mini batch gradient descent. So in batch gradient descent, we consider the whole data set for calculating the gradients and updating weight parameters. So you see, this is the actual gradient we are calculating, right? So this is very smooth. If you start from here, you will reach this is the minimum point, right? So this path, you see, this is very smooth. This is the contour plot of the graph, contour plot of the error curve. And in stochastic gradient descent, we consider one data sample for computing gradient and updating updating weights. So in stochastic gradient descent, you see the graph is very noisy. In mini batch gradient descent, this is a compromise between batch gradient descent and stochastic gradient descent. We get a much smoother than stochastic gradient descent. Now our target is, can we make this zigzag pattern, right? Can we make this pattern little smoother so that we reach to our minimum faster. So that is the target of this optimization algorithms and all these optimizers basically. So I want to reach to the minimum faster. So that is our target. So let's see how we'll do that. So in case of momentum, our main idea is, if gradients across batches point in the same direction, then we can be more confident and take larger steps in that direction. So let's say you are starting at this point and at each iteration we are moving towards this minimum, right? So let's say you are moving in this direction, in the next iteration also you are moving in this direction, and next also this direction, then we can take much larger steps towards this direction. If you are taking different steps, right, different direction, right, first in this direction, then this direction, then we can't use momentum in this case, right? But if you are taking same direction, then we can take much larger steps in that direction. So that's the main idea behind momentum. So what momentum does is, momentum introduces a concept of velocity. So what is velocity? Velocity is instead of using the current gradient, we accumulate gradients from previous states. So if we have to keep track of the direction like in multiple iterations, right? So we have to keep track of the previous iterations, right? So instead of using the current gradient, we accumulate gradients from previous steps. So this is the gradient accumulator. Vt plus 1 is gradient accumulator at iteration t plus 1. So that how we are calculating. Beta times Vt minus alpha times gradient of error. So earlier what we are doing is Wt plus 1 equals to Wt minus alpha time gradient of error, right? So instead of this term we already had, so that is there, but we are just introducing this beta times Vt. So that is the gradient accumulator from the previous iteration. So we are introducing this. This is our gradient accumulator. Now Vt, this is basically what minus. I am writing it in this way: g hat of Wt. So let's say instead of writing this is easier and simpler to represent. G hat or Wt is the gradient at tth update, and our weight update will be Wt plus 1 equals to Wt plus Vt plus 1. This. So earlier we were adding this minus alpha times this gradient, right? Instead of that, now we'll add this Vt plus 1. So that is the change in our momentum optimization or momentum optimizers. So this is the optimizer momentum formula. So now we'll see how we calculate this momentum in for few iterations, because this will give us some insight. So this calculations looks little bit confusing, but it is very simple and it will give some insight. We need that. So these are the iterations. V0 is 0. Let's say we are starting with 0. V1 will be what? Using this formula, beta times V0 minus this alpha times this gradient of the iteration 0. So this is minus alpha times g hat W0. V2 will be what? Using this formula, beta times V1 minus alpha times g hat of W1. So if you expand this, simplify this, we get minus beta times V1 is what? This alpha g hat W0 minus this thing. Let's do this calculation for few more times, or 1 or 2 times at least. V3. So that will be beta times V2 minus alpha g hat of W2. Let's just replace these values. V2 is what? From here, we'll just replace the values. Beta times this, we get minus beta square alpha g hat W0 minus beta alpha g hat W1, then minus alpha g hat W2. So alpha we can take out because this is common. So we get minus alpha times this beta square g hat W0 plus beta g hat W1 plus g hat W2. Can you see a pattern here? If not, let's look at the next slide. So we calculated till here. V3 is something like that, minus alpha and this. So if we just keep on doing this, we get at kth iteration, we'll get Vk is minus alpha times beta power k minus 1 g hat W0 plus beta k minus 2 g hat W1 till g hat Wk minus 1. So this was V3 and minus alpha, beta square, that is 3 minus 1, then beta, then 1, and g hat W0, here g hat W1 till g hat W2. Similarly here for Vk we will get minus alpha times this whole thing, where we have beta times beta power k minus 1, beta power k minus 2 till 1, and g hat W0, z hat W1 till g hat Wk minus 1. So this is, don't get confused, this is, we need this for our intuition. So this is the equation we have got, right? And we can write it in terms of summation, right? So it's basically minus half summation of I equals to 1 to k beta times k minus I g hat w I minus 1. Anyway, so we got the weight update. How it will happen is wt plus 1 is wt plus vt plus 1. So wk is wk minus 1 plus vk is the same equation. Now let's see what we can find from this equation. So here in this equation, this g hat w0, that is gradient for 0th update, z hat w1, that is gradient for first update, z hat wk minus 1, that is gradient for k minus 1 update, right? That is clear. Now let's say if all these gradients point in the same direction, so that means g hat w0 equals to z hat w1 equals to z hat w2, and all these gradients, right, these all are same. So let's write it as z hat simply. So we can write this vk, or let's say vt, we can write as minus alpha g hat times this beta terms only will come, beta times t minus 1 plus beta times t minus 2 till 1. This is the simplified formula we get what when if all the gradients point in the same direction, right? So this is what we got. Vt is this, and this is, I just reverse the order, minus alpha time alpha g hat 1 plus b plus b plus, this is the thing, right? Where when all the gradients are. Now we know about this geometric series, right? So this is a geometric series. So limit summation of k equals to 0 to infinity ak, that is 1 plus a square plus a3 up to an, let's whatever, up to infinity. If you calculate, it will be 1 divided by 1 minus a. So that is a geometric series, we know that, right? So this is the same we have here. So if we compute the limit of this vt, now why we are calculating limit of this vt? Because we want to understand the maximum possible velocity, right? So that's why we are taking limit of vt when t tends to infinity. So this will be what, minus alpha g hat, this thing, it will be minus alpha g hat divided by 1 minus beta, because that is the geometric series form. So this is why this we got simply. So now in normal gradient descent, our formula was like that, wt equals to wt minus 1 minus alpha g hat, right? So g hat is basically when we have the same gradient for all the all the iterations, right? So if we used normal gradient descent, we used to get this formula, or whatever, you can write it in any way, right? Wt minus alpha g hat, right? So but in case of momentum, gradient descent with momentum, we get this, wt equals to wt minus 1 plus vt. What is vt? Vt is minus alpha g hat divided by 1 minus beta, right? So usually we choose beta as a value between 0 to 1. Usually we choose something like 0.98. If you take any value between 0 and 1, right? Let's say you take 0.9, right? So earlier we are getting minus alpha times g hat. Now what we'll get now? We'll get minus alpha times g hat divided by 1 minus 0.9. That is minus alpha times g hat. 1 minus 0.9 is divided by 0.1. That is, you are just getting 10 times minus 10 of alpha g hat. So here this is actually amplifying the step. So earlier just because the value is between 0 and 1 and we are dividing by a value of 1 minus that value, right? So also we'll get a value here that is between 0 and 1. So if you divide by that, we'll get a much larger value, right? That is the coefficient will be for this one. So this is the amplification factor 1 divided by 1 minus beta, right? So that's the main concept of momentum. So if gradients point in the same direction, we take larger step in that direction. right? So my alpha g hat divided by 1 minus beta is always greater than alpha g hat. So and that is g hat. So and this 1 divided by 1 minus beta, this is the amplification factor we are getting. Now one thing is, if you take larger steps, oscillations and U-turn around minima is possible. So if you have like this curve, and if you are just taking, let's say you are taking large step, it's possible that you will take a larger step, will reach here. Then from here you might reach here, there, right? So it might not converge. So that is one drawback we have for momentum.